information is courtesy of AIAA, American Institute of Aeronautics and Astronautics, the Sydney section. We are the professional organization for aerospace professionals. We generally organize events and talks live in Sydney, in Canberra, and in Adelaide. However, due to obvious reasons, then we've moved them online and made them accessible to the wider audience. If you are interested in joining AIAA, please do check the website, AIAA Sydney, and there's also an AIAA Sydney section webpage. Feel free to visit. Just so everybody is aware, this event is recorded. It is going to be available as a recording on Facebook. It's recorded live on Facebook, and it will be available on AIAA archives for all the members to see and listen. Dr. Kruzins is going to present his talk. You can submit questions at any time. Please submit the questions to me. I will then pass them on at the end of the talk. And AIA board, everybody from AIA board in Sydney, please do stay on afterwards, after this meeting is over. Right, that's the house cleaning stuff happening. Now, I can start with a proper introduction. So like tonight, our speaker is Dr. Kruzins, the director of NASA operations in Canberra Deep Space Complex. Dr. Kruzins is a long time supporter of our AIAA, and actually his last talk he did for AIAA was live 2 years ago, almost to the date. 2 years ago and 2 days ago, actually, if we're accurate. Dr. Kruzins is the current director of the NASA Deep Space Complex and has been for the last 8 years. Before that, Dr. Kruzins grew up in western suburbs of Sydney, in an immigrant family, and got his astrophysics degree at University of Sydney, and later on his PhD degree at Southampton Uni in UK in aerospace engineering. His professional path is very wide and very varied. I'm not going to go through it all. I just want to do a quick rundown. If you would like to check his bio, please do. It's on the CSIRO personnel site. His professional part did start at BAE Systems, working commercial and military satellites, and especially the Galileo constellation. He followed that with Defence Science and Technology, the SDO, which most of Australians, you will know about it, where he played quite a few key roles in engineering. That stint was followed by his first round of deep space work at the NASA Deep Space Complex in engineering as an engineering department site manager. After that, he continued on the Department of Defense on the Director General of Capability Science, where his main task, where they were involved, not just main task, but generally involved in analytics of defense acquisitions and general capability.
Poor at these sorts of things. You'd think you wouldn't be, but I am. Let's see, I've got that. Is that sharing now?
It's sharing.
Okay, I'll just put that on presentation mode. Slideshow. There we go. That's better. Is that all good?
Yeah, it's working.
Okay, thanks so much. And I've got to give a big shout out to my friend Simon Pashby, whom I haven't seen in 10 years online there. Hi, Simon. Thanks for coming tonight. And I'm sure there's a lot of other friends out there as well. Thank you for supporting this evening. So let's talk about the Australia's role in NASA's deep space exploration missions and what we do here in Australia working with NASA. That station on the right-hand side has been there since 1965. So it's over 55 years. And Australia's played a great role in deep space exploration as part of the NASA missions. The station is cradled between the Brindabella Mountains and the Bullen Ranges. And there's a good reason for that. And the primary reason is because it provides an excellent radio shadow from Canberra so that we can listen to the whispers from space. So let me go to the next slide. So just in a nutshell there, some of the key parameters. I will mention that tonight's a little bit different to the past presentations that I've done. I'm usually talking about space missions carried by CDSCC and some of the scientific results, but tonight's going to be a bit different. I'm going to cover more about the station itself, some of the engineering, some of the new projects coming through, and how we survived the bushfires that we came through late last year, and then a pandemic. So we've all been through this nightmare, and I'll just give you an idea how we survived it, or are surviving it at CDSCC. But in a nutshell, on the right-hand side, you can see some major figures there. So we've got about, in fact, 89.35 staff, about 90 staff. We've got a couple of people who do part-time. We control something like about $18 billion of assets in the sky. So a lot of responsibility. Something like about 35 or more spacecraft missions from all parts of the world, not just NASA, but also the European Space Agency, the Japanese Space Agency, and even recently the United Arab Emirates in Israel. Our annual budget is about 20 million Australian dollars a year, although it goes up and down about a couple of percentage points. And we host something like about 10,000 school kids through our visitors centre at CDSCC. It's space appears to attract something in the Australian psyche. Maybe it's exploration spirit, I'm not sure, but it does. And we get a lot of school kids and other public coming through. So that's roughly us in a nutshell. Let me talk about us in the network. So we're one of 3 stations in the NASA network, operated entirely through NASA, operated by JPL for NASA, and we manage the Canberra station here in Australia through CSIRO. So I'm a CSIRO employee, I'm not a NASA employee, and we've got 90 very proud Australians who actually provide this role here in Canberra. So it's supports interplanetary spacecraft missions. We also do radio and radar astronomy observations from here, but that only forms about 10% of our program. The space exploration missions are most of it. The Deep Space Network, with our sister stations at Goldstone in California and Madrid at Robledo de Chevella, plus our colleagues at JPL in Pasadena at the headquarters, constitute about 500 employees worldwide. And we're a very close-knit family. Once you join the DSN, you never leave it. Oh, and I should say it's the largest and most sensitive space telecommunications in the world. So let me go to my next slide here. I had to put a bit of this legal stuff in here, so if there's any legal people out there, you can understand how the relationship is like. So we actually operate under a treaty. So we have American assets located on Australian soil, which requires the need for a treaty. So the Space Tracking Treaty has been operable for a long time. We've just renewed it for another 25 years. So that was renewed in February 2018. So we're good to go to 2043 to continue working here. Underneath that treaty, we have what we call an agency-to-agency agreement, which identifies the CSIRO and NASA as the 2 entities in Australia and the United States. And underneath that, we have the ability to flow money. So that is a contract. So the contract is the exchange of funds. So it looks rather convoluted and complicated down there. It's not really. The day-to-day management of the whole network falls to the Jet Propulsion Laboratory, and we receive directions from them at CDSCC, as does our Goldstone and Madrid sister stations. So that's roughly how it works. And it's been in place for a long time, and it works very well. So one of our primary functions, getting into a little bit more complication here. So there's the main ones on the right-hand side. Telemetry tracking. So we take data down from, digital data down from the spacecraft, which are in orbit or which are going to planets around the solar system. We take the engineering parameters from those spacecraft. We also take the data from cameras or electromagnetic measurement devices or other systems on board the spacecraft and send them down to Earth. We collate them at either Canberra or Madrid or Goldstone, depending who's pointing where, chop them into ones and zeros, and we send them off to Jet Propulsion Laboratory, then sends it off to the mission managers across the United States or other countries around the world who then create the scientific discoveries. We also do tracking. Tracking means determining the position of the satellite or of the space mission, determining how far away it is, what angle it's at. It also takes into account how we're pointing, antenna control, and we call all that parameter tracking. Command is about sending actual commands up to the spacecraft. And it's not uncommon for a mission to have its software updated while it's in orbit. And in fact, that happens, that's going to happen particularly for the Mars 2020 and also the rover missions. So it becomes a spacecraft at launch, but as it gets nearer to Mars, it gets its software uploaded and it turns into a rover just before it comes down. So sending commands up to the spacecraft, telling them to move in different directions or trajectory control maneuvers are a standard routine. We also monitor our own parameters of our own antennas to make sure that we're doing the right things. Our frequencies are set correctly, our pointing is correct, and our bit rates are correct. And we can even see, in fact, we do control the other antennas in the network in Madrid and Goldstone. They control us as well. And I'll talk about that in a minute. It's called follow the sun operations. The other thing we do is interferometry. Interferometry is where you take multiple antennas on the ground and taking a signal, and then you can work out, for example, in radio astronomy, you can cross-correlate those signals and then improve your reception of the signal you're taking. If you have a fixed position in the sky and receive at various antennas on the ground, you can determine how the ground is moving. So we use some of that for geodesy work as well. And the other things we do are radio astronomy. For example, work at CDSCC is looking at active galactic nuclei, and we're also cataloguing radio sources as reference points. And some of the work that Shinji Horiuchi is doing as well is related to water mason mapping around black holes. And another bit of work we're doing is near-Earth asteroid observations. A little more recently, but the capabilities at CDSCC and our other facilities in Australia, including the Australia Telescope National Facility, is able to do bistatic radar of near-Earth asteroids. And I'll talk a bit more about that soon. So follow the sun operations. This looks complicated, but it's not really. Prior to 2017, each of the stations, either Madrid, Goldstone, or us in Canberra, would be completely autonomous. We could track our own spacecraft that we could see in the sky. And as the Earth moved, we picked up another set and picked up another set as we moved around. And the stations didn't talk to each other too much, only for information reasons. That completely changed in 2017, where we went to a concept called Follow the Sun. Follow the Sun is the station in daylight controls the other two stations at night remotely, including all their antennas and parameters and everything else. And as the station in daylight goes into darkness, it hands over its control to the next station, which then controls. And it goes around in a loop like that for 24 hours. So for 9 hours of the day, we here in Australia control the entire network of the deep space antennas, 12 antennas around the world, and have complete responsibility for ensuring the downlink of the missions that we track, of which I said about 35 missions. It required us to, I should say, JPL and NASA to come up with novel and fail-safe systems. We played our part with the software in that as well. That was all successfully implemented in 2017 after a long gestation of several years building the software so it was fail-safe. And it works very well. It's now routine. Happens every day. And we've been doing that for the best part of 2.5 years. So the next slide will show you a picture of what we did for our Operations Control Centre. So we started building that in 2016. We had a tiny Operations Control Centre. We've now got something 4 times as big or more. That Operations Control Centre was commissioned in 2017. We said goodbye to the old library document centre we used to have. We put about a $1 million facelift into that. And we said hello to a new Operations Control Centre. And you can see it down the bottom there. It's quite a state of the art. Each station, there are about 10 stations there. Each station controls, and you can see 2 antennas. There are three banks. I don't know if you can see my little arrow there, but you can see there are 6 monitors there. Each bank controls 1 antenna. So sitting at that console, the operator controls 2 antennas at once, and that's called 2 links per operator. So the operators will sit at their consoles, 2 links per operator, controlling all 12 antennas. There is a plan in 2020, late 2020, to go to 3 links, which will require us, it's more complex, more software, but it will deal with the growing number of space missions that are out there and I would say, a relative shortage of apertures to meet those missions. So this is real juggling going on here now. Going to the next slide, let's talk about the antennas a little bit. So these are what we call our beam waveguide antennas. They're a 34-metre diameter dish. They're quite big. These represent, I suppose, next generation dishes. So some of the dates on these, the DSS-34, although we call them next generation, that was commissioned in 1997, but DSS-35 and DSS-36 were commissioned in 2015 and 2016. And I have to tell you, as director of CDSCC, it was such an exciting time watching those antennas built on the bedrock of the granite, which we're famous for in the Tibimbilla Valley. So they are very stable, locked onto that old granite shelf. If you have a look, why are they called beam waveguide antennas? Well, have a look. I don't know if you can see my arrow or not, but if you look at the center of the dishes themselves, you'll see a little pinhole going down there. Do you remember your single lens reflex cameras? What happens here is the signals come down, they reflect off the dish, they hit the sub-reflect in the middle, and they bounce down those little holes. Then they bounce along a bunch of mirrors and disappear 2 stories underground to be received by low noise amplifiers cooled to liquid helium temperatures. And that's why they call them beam waveguide antennas, because all the conditioning of the signal and receiving and transmitting is done below ground, which is fantastic if you have to fix those antennas during a Canberra winter at 2 a.m. in the morning. You do not want to be going up on the dish surface doing that. You can actually do a lot of the work underground in air-conditioned comfort, where it's nice and safe. So each of the deep space stations has 3 of these. We have 3. Plus they have a large 70-metre antenna. Whoops, hang on. I'm going to go to that and I'll go back a bit. Plus a large 70-metre antenna. This is our one called DSS-43. That is big. It weighs 8,500 tonnes and it is the largest steerable parabolic antenna in the South. And I've gotten ahead of myself. I'm going to go back 1. Now, let's go back to the beam waveguide antennas again. So you can see I was talking about commissioning in 2015, 2016. So that took us about 4 years. So I'm going to show you how to build an antenna in 30 seconds. So I'm hoping this is going to work. Let's see. So we've dug the hole, big ground. We're on the bedrock. This is what it starts looking like. So you put the concrete in, you put your ducting in the side, you fill it up, you then start building the pedestal area, put it together, you build the dish surface next to the ground next to you, and then you start putting panels on the dish surface, and then you have a large crane which puts that dish surface on top. And all that just took about, I'll run it again because it's kind of fun. All that took about 3.5 years. And I have to tell you, one of the scariest things to do as you're a director of a facility is signing off on the explosives permit to blow the granite away so you can create a hole big enough to put this thing on. So that was the construction of DSS 36. The actual antenna materially was constructed in Spain, assembled there like IKEA bit of furniture, disassembled and shipped to Australia, and we reassembled it out here with support from General Dynamics, JPL and CSIRO. So let me go to the next slide. This is DSS 43. Now, why? This is an interesting one. There are only 3 of these in the world, and they are quite unique. And we've just been recommissioning or rebuilding DSS 43. And for most of this year, we've been working on the transmitters, receivers, the HVAC systems, electrical switchgear, and a number of other systems. And this is a unique antenna because it's the only antenna in the world that can communicate with Voyager 2. And if you know, the Voyager series of spacecraft were the ones launched in 1977, which saw past just about every planet in the solar system beyond Earth except for Pluto, and got the most fantastic scientific data. But Voyager 1 went north and Voyager 2 went south. And Voyager 2 went so far south that no one else can see it now, apart from DSS 43. And it is a long way away at the moment. But to make us continue operating with this huge dish, we've had to rebuild it. And this is some of the work we've been doing this year. So we're replacing one of the central conical sections at the top right of the image. We have replaced, when you see S20 and S400, don't be too frightened. That's S-band frequency 20 kilowatts and S-band frequency 400 and that's the amount of power required for the transmitters. They've been replaced with S-band 100 kilowatt and 20 kilowatt systems with another X-band 80 kilowatt system put in. To do that, we've had to take that conical section out, put it on the ground, and then put the new transmitters and low noise receivers in. That was considered to be the safest and easiest way to do that. In the past, they did it up on the dish, and I shuddered to think how hard that would have been. But that's been going on this year. We've got to get our first signals back up to Voyager 2 by about October. If we don't, it could be a problem because it has a timeout on the computer on Voyager 2, so we want to get a signal into that before it goes into safe mode, which could be a problem for Voyager 2. So we're working very hard over the weekends during COVID and other areas to make that happen. So I'm going to show you a picture, or rather a movie, of us lifting out one of the conical sections, which happened not that long ago. This is just a couple of months ago. It's not very long, and it was taken by one of our JPL fellows who was on the dish surface of 43. And there it is. There's a huge crane that's across there, 57 metre span. Now lifting quite a hefty bit of weight there and lifting it out quite safely and putting it out. It's a short video, so I'll run it again in case you blink your eye. There we go. So we pop that thing out, we pull out all the old equipments out of it, disconnect all the cabling, of course, and then we put it down the side and repopulate it. Oops, let me go down one. And so once you've got it on the down and fixing it all up and put the new bits of equipment in, you then have to put it back. So this is a picture taken from our visitor center. Lifting it. So the operation went pretty quickly, pretty smoothly. I'll run that again for you. I don't have to put the music on it. It's very invigorating. But here we go. So this was an exercise in project management because we had a window where we booked the crane, and there's only a couple of these in the Southern Hemisphere. So we had this tight window to make sure we got everything ready for the crane to lift, and luckily we got it all in there. Although COVID did frighten us a little bit because we were wondering if we had any issues on the station that could really throw the schedule out. But luckily, since about February, when we started, we have had no incidents on the station and things have proceeded relatively normally. Hang on, I'll go to the next one. So these are some of the highlights. These are a little bit older of some of the space tracking highlights we've had on the station. So this is one of the very interesting missions we've been tracking for a very long time, over 11 years, was the mission called Dawn, which went to the asteroid belt and visited the two largest objects in the asteroid belt, Vesta and Ceres. And they announced end of mission in 2018. And I don't know if you've been following the scientific discoveries from there, but there seems to be some kind of evidence as potential for cryogenic type volcanism, possibly on one of those. But I'm not a specialist here and I'm not going to make conjectures on it at this stage. Kepler was a nice mission, a lovely mission to watch. It wrapped in about the 20th of February 2019, that's just not long ago, and observed something like about 530,000 stars. It detected 2,662 exoplanets. Now that was replaced by... Sorry? Any questions out there? Okay. And that was replaced by TESS. It's called the Transiting Exoplanet Survey Satellite. And that is extending the work that Kepler did, looking at further exoplanets, and discovered another 2,100 with 66 certain ones and another 2,000 under review. So the universe, rather I should say the galaxy, is populated. Everywhere we look, we find planets, which is just mind-boggling, just how much there is out there. And of course, Voyager 2, I mentioned, that entered interstellar space after 41 years. And on the 5th of November 2018, announced interstellar. And we used the Parkes Radio Telescope as well to look at the signals coming back to determine when it crossed the heliopause. And the heliopause is the position where the solar wind and the galactic solar winds actually meet and form a shock layer. And that is the first spacecraft ever to go into interstellar space. And we have the honour of tracking it here in Australia. So let me go to the next slide. So what's the future looking like? Well, just recently we had a really exciting time. The United Arab Emirates had launched its Mars mission, and we were fortunate enough to be supporting the tracking of that when it was launched and in its early orbit phase. And it's now safely on its way to Mars. And then Mars 2020, which is the next rover. So LEOP is launch and early orbit phase. And we picked that up on the 30th of July, something like about 10 p.m. at night. And our antennas were controlled through Follow the Sun by our colleagues overseas, but they're our antennas. And that was put in a near perfect launch on the way to Mars. We had a little bit of delay getting the telemetry lock up, but in the end, it all worked out fine and it's on its way and looking very good. And we're looking forward to that landing on Mars around about the 19th of February in 2021, which would be really, really exciting with the Perseverance rover, which has a helicopter on board. Imagine that, a helicopter flying in 1% atmosphere on Mars. We've also got the Hayabusa return coming up as well on the 6th of December. That'll ranter over South Australia. And we have the Emirates mission going to Mars orbit insertion on 9th of February. And some really major programs coming up next year. The James West Space Telescope, looking like it's going to launch around the 31st of October 2021. We'll provide tracking support for that. And another really interesting one called DART, which is a double asteroid redirect mission. And that is going to demonstrate a kinetic device used to impact an asteroid to see if we can deflect it. The asteroid's going to be called Didymos, and it's about 780 meters in diameter. So this is part of an initiative for planetary protection, I would call. So if we do have an asteroid heading our way, this mission is to see how much they can deflect or make any kind of movement in that. It almost sounds like a movie, doesn't it? But it's real, that these kinds of missions are going ahead. Which takes me to my next slide. This is some initiatives that we've been doing here in Canberra, working with our colleagues at the Jet Propulsion Laboratory, and also CSIRO and the Australian Telescope National Facility, and also our colleagues at the University of New South Wales. And the idea here is that we illuminate an asteroid target with the big antenna I was telling you about at DSS-43 at high power, and then we observe the reflection of the asteroid at somewhere like either Parkes or maybe the Australia Telescope Compact Array in Narrabri, depending on the frequency we use. And in doing that, we can get a better estimate of the orbital parameters of those asteroids. And a number of asteroids, probably 5 to 7%, are not detectable from the Northern Hemisphere. And the two main workhorses for asteroid detection in the Northern Hemisphere are the Goldstone antenna in California. That's my phone going off. I'm going to have to ignore that. And also the Arecibo antenna in Puerto Rico. Now, I don't know if you're aware, but Arecibo suffered a catastrophic event not long ago where one of its cables broke and brought down and fell into the valley of it. And they're going to be offline for nearly a year. So that leaves, and with the 70-metre antenna still being repaired, also, that doesn't leave a lot in terms of what's looking at into deep space at asteroids. So we've been doing some work on this since 2015, just doing some R&D work just to see if we can do it. And we have tracked something like about 8 asteroids now since 2015. And some of those are there on the left. Some big, some small, ranging out to 0.7 lunar diameters down to across to 7 lunar diameters, and anywhere between 20 and 400 meters in diameter. So those can get pretty big. I bet you that's Jill's mum from the United Kingdom phoning. She has perfect timing. Okay, let me go to the next one. This is a little bit hard to read, and I apologise for that. So this is surviving the bushfires in 2018, 2020. So in 2020, we had the Royal Valley fires at Namadgi National Park. Something like about 80% of the park was burnt. And 22% of the Tidbinbilla Nature Reserve, which is something like 1,444 hectares, and 3,350 hectares of rural lands burnt. And the fires came in 6 kilometres of the Tidbinbilla site. So that kept us awake at night quite a lot. How do we keep our people safe? Well, the important thing, we learned a lot of things out of that. Regular communications and prevention work with our staff, status updates regularly with people, ensuring our parent organisations, CSIRO and JPL NASA informed. We established great relationships with Rural Fire Service, in particular the emergency services in Canberra. And during the fires, we also, at Pierce's Creek Fire in 2018, which also came close, we had direct ComSend contact with some of the aircraft, which was very handy because we control the airspace. It's called R430, A, B, and C around the zone. We do that to prevent aircraft flying when we're operating a high-power transmitter or doing any radar work. During the fires, we did a lot of evacuation planning, and we also engaged the assistance of the Department of Defence, who came out and helped us with clearing a 12-metre perimeter. So this got really serious for a while, and the winds kept blowing left and right, I should say east and west, as it was zigzagging down the mountain, and it was quite a time for us. We prepared evacuation plans and safe areas as well. So we were prepared to put the station in stow and leave it if things got really bad. But luckily it didn't go that way. Now, my next slide here is, I'm hoping it's going to work. It actually is some pretty interesting footage taken by our ops supervisor, Richard Stevenson. I'm going to see if it works, of an aircraft dumping retardant I hope that. Fingers crossed. So this aircraft was firebombing the Namadgi area in 2018, Pierce's Creek, which also came close to us, to our northwest. And we were watching the fires. The smoke was drifting over the station. That's the collimation tower behind you. It's dropping fires on the road next to us. That is DSS 45 right there. How close it came. So we really thank and take our hats off to the crews of those aircraft.
Hi, Ed. Sorry, we can't see the video. I think you're only sharing the presentation. You might have to change screen.
Oh, okay. I'm sorry about it. I wonder if I can do that. How do I change screen?
Share screen and click on
Right.
Back, Ed. Now, before you minimize anything, can you see all the little icons in all our videos?
Yes.
Great, great, great. So at the bottom of this screen, you should see a big green button that says share screen.
Yes, got it.
Great. That's the one you want to press.
Exactly. And I've got the presentation here and I'm going to click on share.
Great.
I think we're back online.
Thank you so much, Mike.
No worries. We've all had Zoom nightmares. Trust me, I've had my own this week. So we all feel your pain, Ed.
We rehearsed this before we did it and it all worked sweet. No, it hasn't. But anyway, coming back to it. Okay, so if you recall this video, let's go further down. Done that one, done that one. We've done that one and that one. I'm not going to click on but it's a really dramatic video. If you do get a chance, go on the internet, type in Pierce's Creek fire and you'll see something like a C-130 flying over the DSS-45 antenna. Apologies for that. Didn't test that one out, should have. I'll go to the next one. Can you see that one? Japanese looking thing?
Yep, can do.
Okay, great. All right, I want to tell you about this because it was so special. So the Komagani school in Nagano in Japan visited CDSCC in October 2019, and occasionally we have international student groups coming out and we show them a little bit about what we do, what NASA does, what CSIRO does, what JPL does. And we actually take them for a tour around. And a lot of the kids are so impressed about what we do that when they heard that we had the fires in Australia, which went around the world, they were really upset about the loss of wild animals and things in Australia. And off their own bat, they raised money for the animals in Australia, and in the way they did it, they raised money by making lanterns and little gifts and things like that in Japan. They sold those and they raised the money for the Suzaka Zoo in Nagano, which is known for its red kangaroo program. And that's established conservation programs together with the Aquarium Association of Australia. So they raised something like about 10,000 Australian dollars, which I think is just brilliant. And the picture on the right-hand side just shows the little poster they made and sent to us with a lovely picture and letter from the principal of the school. And this is some of the kids here. And they sent the pictures to us. And we thanked them quite heartily and warmly for just the way they were thinking about us and thinking about Australia and thinking about the animals that were lost. That was a nice story. Going to the next slide. How do we survive COVID-19? My word, it's been such a weird year going on. We were expecting the locusts to come next. But what do we do to keep operating? Well, the NASA put together a continuity of operations plan called the NASA Pandemic Continuity Plan. And we followed that. And it was a site-level pandemic monitoring team was established. We cancelled all site visits. We closed the visitors centre. We had about 15 staff working from home. We established high-range stations, and we split our shifts, and we actually did everything possible to avoid getting anything to do with COVID, and we were quite successful. We've been able to maintain normal operations and even do all the rebuilds that have been going on in DSS 43. We isolated our operations room and did a whole bunch of things. So far we've been operating very well. The only impact on DSS 43 has been about a 4-week delay due to the problems with getting people on site and off site due to COVID. By noticing the time, I'm going to try and go a bit quicker. Look, the next slide is about the solar power project in 2021. I can't think of anything cooler than exploring deep space with a green facility. And that's exactly what we're going to do. 1.2 megawatts of solar power. And if you look at the picture on the right-hand side, you can see these little striations in the ground. That's somewhere around about between the DSS 36 antenna and DSS 45. We're entering into a solar power purchase agreement where we actually just buy the power with another owner who will actually own it. With the 30% increase in power bills that are happening in Australia in the last year or so, we're going to save something like $300,000 a year. So our power bill, you can guess, is something like about $1 million or more just operating those antennas. So that's an extra saving, and it's a really fascinating project that's going to be coming our way soon. Optical communications is the future. In the next 2 decades, NASA are proposing a laser-based telecommunication systems across the solar system. And we're working with our colleagues at JPL to look at an optical hybrid antenna concept, which could retrofit the 34-metre antennas with mirrors. So that the first 8 metres of the antennas have a coating on them, which will reflect optical light in 1550 nanometre. Early days yet. Our small role in this is to collect the weather data over CDSCC to see what the effects of cloud and weather is going to be on the laser channel as it goes up from the ground to the sky and back down again. And I'll move on because I'm running out of time because we need some time for questions. And that's it, really. So the future's looking really bright. Optical communications, asteroid work, tracking 35 different space missions. And it's a real privilege to work there. And thank you so much for listening, and deep apologies for my lousy finger control of Zoom.
Thank you very much. If anybody has questions, can you please send them to me? And I will shoot them forward so we don't get swamped. All right, we've got... so we're just going to... questions take time to type, right? So I was just going to see if you have any other anecdotes, interesting anecdotes from just the last year. Must have been quite interesting.
Well, it's been a very tough year, to be honest with you. The pandemic's been tough on everyone, and including all the work we're doing as well. And we're hoping to get through this stuff. We have plans for living with these sort of pressures, and I think it's all going to be good. An anecdote is we are looking at rebuilding our visitors centre. That's been there a long time, and we're thinking about rejuvenating the... if you come out there, you'll see pieces from all the Apollo days. We have a moon rock out at CDSCC. Unfortunately, it's closed at the moment. But when things do get better, it's a fascinating exhibit run by our Glenn Nagel. And we're going to rebuild those buildings. We're hoping to rebuild those buildings and put something much newer in, which is going to be far more visitor friendly and will hold more exhibits. So that's one thing that's going on. What else? Ooh. Well, I guess we're just getting ready for all the future space missions that are coming through. One of those will be the Artemis program, which is the Lunar Gateway. As you know, our NASA colleagues are going back to the moon together with other international agencies. And part of that program will be to launch a vehicle which will be in lunar orbit. And we at CDSCC and also the Deep Space Network are very fortunate to be able to have the nickel for actually carrying those human spaceflight signals back to Australia and other parts around the world. So that'll be humans back to the moon. And once again, here we are, we'll be carrying signals through Australia for that, as we did for the early days of Apollo and Gemini and other programs like that.
Thank you. That's sounds like you guys have a lot of work ahead. We've got a question from Morali. If you could please put up a link for the waterbombing flight, so we can all copy it down and have a look. You can just reshare the screen if that works.
Okay, I can do that for you.
And in the meantime, Andrew Neely is wondering, why is the 9-hour window rather than just the 8-hour window? Is there overlap on each side?
Yeah, precisely right. We need an overlap between the stations so we can let them know what we have changed, what we've done, what to look out for. A little bit, and that's exactly why we do it. So that's correct. I'm just going to find this slide for you. And that's it there. So if you want to write that down,
it's okay.
There we go.
So we got.
So if you want to write that down, there it is.
Thank you. Is there, Eric's asking, as a non-STEM young professional working technology consulting, what skills are best to build up to be involved in the program, to be involved in CDSCC?
Oh, okay. Oh, well, I got to tell you, there's a mix of people at CDSCC, and a lot of technical type people who are specialists in electronics and electrical work, a lot of technical trade type people as well, because what we do is very bread and butter. Diesel mechanics, mechanical people like that. But we also have professional engineers, electronic engineers, electrical engineers as well. We have one scientist there. To be honest with you, we don't wear white lab coats. We're not scientists. We're just people that keep those antennas operational. The operators themselves receive many years of training. In fact, we've got people who've been there 20, 30, 35 years. It's a place when you come to, you build experience up. You don't get the experience overnight. It takes a long time to do it. How to get a job there? Oh, dear. It's a question of being a little lucky, having the right skill set, looking at the job adverts at the right time. We don't get much of a turnover out there. People tend to stay a long time. The manager positions, again, people have been there a long time. I can tell you about my own example. So I began as a physicist. I then did engineering, spacecraft engineering for a while. Came back to Australia, worked with Defence for a while, and I just happened to be looking at a job advert at just the right time, and it came up, and went for the interview and got the first role as engineering manager. So there are basically two levels. There's a tech trade level, and there's also the engineering level. So people who can actually do things with their hands and can design things related to radio frequencies or mechanics or whatever, this sort of thing, can open a door for you. You can also look at internships overseas. Jet Propulsion Laboratory does that sometimes. You can look at that. That might open another door for you. But yeah, I hope that answers the question sort of. It's kind of a bit luck, I think.
So I'm just going to follow up from this question, another similar question. Morales' question is, as a young researcher, what career paths are available at DSN, a Deep Space Network? Because it ties in with what you were talking about now.
Okay, well, we don't take internships at CDSCC, but the CSIRO does. They do take. There are opportunities in CSIRO for people to come through. There are also places at JPL occasionally, although being an American citizen helps a lot over there. But they do take international people as well. And that might open a door in the scientific mission area, which could then open a door in the DSN. But the DSN, I don't think, takes too many graduate type people. It tends to be a very operational facility. So, gee whiz, that's about the best I can offer at this stage. But what I will say to you, if you're keen on doing this stuff or being in space or being a space designer, get a background in either engineering or physics or both or mathematics. Do well, never give up, keep going for the space jobs, and I guarantee you will get there. Never give up. It takes a while though.
Thank you. Right, so we've got a question from Bill Barrett. What laser frequencies are planned for the optical comms? Is infrared being considered to pass through the cloud cover?
Right. Yeah, Bill always asks the hard questions. The frequency is considered a 1068, 1064 nanometer and also 1550 nanometer. Now, the selection of those is an interesting one. Some of those will pass through the atmosphere reasonably well, but cloud cover, even thin cloud cover, will cause a lot of attenuation. It's a real interesting trade-off. It depends on the cost of the equipment and also the laser powers you can get and how sensitive the sensors are at the end of the day. And also it's a safety trade-off as well. 1550 nanometer is pretty safe to the eye, but at much higher powers, you've got to be careful. So that's a driver here as well. And uplinking at those bands as well, you have to be very careful. In fact, you have to get coordination on that in case you dazzle sensors. So there's a lot of work to be done still on going from prototype and theory to practical examples, running these things from the Earth. Running them up to low Earth orbit, there's already a lot of work being done in Australia on that at the moment with the ANU, us and other universities around, University of Western Australia, University of Adelaide, South Australia, and University of New South Wales, I think I mentioned. So there's a lot of work already being done in Australia. Australia wants to take a niche in that area as well because we're good at communications. But there's a lot more work to be done understanding what atmospheric effects affect the optical channels, in what ways, how does it bend the signal, how does it attenuate it, and how does it fracture the signal. And the problem gets even more acute if you're sending it to Mars because the signal strengths then become very, very low by the time you've transmitted from Mars. And if you uplink, you're uplinking a lot of power. So we're still in the very early days yet for deep space on that, but it's coming.
Right. Lovely. Right. So it's 8 o'clock, so I'm just going to do a couple more questions. Geraldine's wondering, does CDSCC support only public sector missions, government, NASA, or can it also support commercial missions for private sector?
Yeah, good question. At the moment, it's government missions, and that's why we have a treaty. It's government to government. So that's the key driver at the moment. Private missions, I probably can't answer that very well. I'd be putting words in the mouth on NASA, but it's not what we're doing at the moment. So it's pretty well government missions at this stage.
Brilliant. So last question. What is involved for operators when they're monitoring multiple antennas?
Oh boy. I wish some of my operator friends were here because they'd tell you. They have a very heavy load, essentially, but most of it is supported with software now. So I think I heard a statistic that to set up an antenna, to set right pointing, predicts, frequencies, Doppler shifts, all that sort of stuff, there's something like 200 commands they've got to put in. Correct me if I'm wrong, operators. But a lot of that's done by scripting now. We have some specialists at CDSCC who have become experts at this for the Deep Space Network. They have a system called the TDN, which is the temporal DSN, correct that. But it's essentially a methodology by which you can script in and simplify the commanding for each of the antennas. That helps a real lot. Our JPL colleagues also have automation software that makes that setup quick, but the operators still have to monitor those antennas. So I guess the way the analog would be, okay, so a pilot can drive an aircraft and you can put on autopilot. Yep, that happens a lot in the DSN. If something were to go wrong, the operator can step in quickly and work out what they need to do. And each antenna has its own little quirk, although they're all pretty similar. And each spacecraft has its own quirks as well. So you tend to get to understand those as an operator. But I don't want to put the words of an operator out there and get it wrong, but they've got a lot on their plate usually. And it's quite impressive seeing all the stuff going on their screens, setting up powers and thresholds and all sorts of things.
All right, thank you so much, everyone. It's 8:05, so we're gonna wrap up. I would like to, on behalf of AIA Sydney section, I would like to thank Dr. Kruzins for this wonderful talk and good questions from the audience. Really appreciate all of you listening and asking. We're going to wrap up. I'd like to ask the AIA committee members if they can stay online for another couple of minutes. And to the rest of you, thank you and have a good night, and see you at our next talk, which will be published soon. Thank you.
Thanks, everyone.